Oh, there's one. Okay. Well, let's at least get that much submitted in. Maybe the rest will follow. Good afternoon, everybody. Hello. I hope you had a great, fantastic weekend. There is a boatload of snow outside, just waiting to be turned into something. I mean, this is perfect snow for making snowmen. Snow forts, you got enough. I mean, you just build up a little pile and carve out the middle. Got an awesome little snow fort. I'm thinking of making one out here with the giant piles from the from plowing the parking lot. Great big mounds. It's awesome. Like a snow castle. It'd be great. But before we can go there, we've got some geometry to do. Okay? We finished our problem-solving chapter, so now we are fully equipped with problem-solving techniques and with the basic skills and knowledge from last semester, which we quickly reviewed at the end of the week, right? To now start combining those elements together to solve more interesting scenarios, okay? And so that's what we're going to be doing for most of the rest of the semester, is taking a look at these much more interesting geometry questions involved in exploring and seeing what we can do with them. Okay? Your grades for the test they should be all in. I'm pretty sure everything is updated there, so have a look at that on PowerSchool. If you have any questions about it, feel free to email or ask me about it. I had to. It's a tricky thing when you got to like grade a simplified thing, but turn it into 100 points worth, so the scaling might not always make sense. But you can ask me about that for more detail if you want. For today, though, we are going to dive into the next section. We're starting now chapter 2 of our text, which involves the basics of geometry, measurement, and shapes, introducing that into the situation. And we start with section 2.1, undefined terms, definitions, postulates, and then finally segments and angles. Because before we can do anything with this, we got to make sure we're all on the same page about where this comes from and how we are building towards stuff that we actually know. Or, in other words, how do we know something is true? Remember, first semester we started with the logic arguments, right? And that is ways to take known true statements of facts and determine other true statements of facts. But we want to go one step deeper. How did we get to those starting issues in the first place? That's where this axiomatic structure comes in. Okay? Everything we know about mathematics and geometry in particular, I don't know why we always focus on this in geometry class. It applies to every math class, algebra included. Okay? Everything we know can be stated as a type of theorem. Okay? That is, a theorem is any type of statement of a relationship, or if I wanted to go broader, right, the definition of math that I've used before, it's those interconnected ideas, a study of structure, statement of relationship or structure, property, the commutative property of addition is a theorem, okay? It's a statement. It's not a theory in the layman's sense of, well, it might be true, that's my theory, but I'm not sure. No, we are absolutely sure about these theorems, okay? They've been tested. What hasn't been tested, per se, is the postulates or axioms. And these are still true statements, but they are so simple, they cannot be proven. Okay? I can't dig down any further. A theorem I can base on, well, how do you know that? Well, it comes from this property and this structure, and you put those together and you get this relationship, right? At a certain point, there's only so far you can drill down. Okay? It is the atom of mathematics, is these postulates and axioms. Everything is built out of those. Except even that's not true. We know that even atoms are built out of something further. And in order for these postulates and axioms to make any sense at all, you have to have the right definitions, right? All of those words that comprise the statement themselves, those words have meaning, right? That's the problem with words. They mean things, right? So the definitions, give meaning to terms. They help us create a common language so we can talk about what eventually becomes the relationships between things, right? And as the textbook kind of indicated, the problem with definitions is that every definition depends upon the definition of something else, right? You look up grubcool in the dictionary and be like, grubcool, right? A pool containing several segments of block. You're like, what's a block? Okay, block. Like, block, individual elements of a grubcool pool. And you're like, what? Right? These definitions are circular. Eventually one has to lead back to the other, right? You can't define a word without using other words. English might be okay with that. In mathematics, we are not. We say we need a starting point. So we have decided on some undefined terms. Okay, these are things described, okay, observed, but they are not defined. They just are. And we say you have to start with this and accept that I can talk about it, right? The undefined terms of geometry are points, lines, and planes. We can't define a point as in say, well, you know it's a point if it meets this specific criteria. Because those criteria rely on further definitions and all those things. They all build out of points. Point is the starting point. But this is common for most subjects, if you really think about it, okay? Everything you study here in school has a method of knowing truth, okay? Science has the scientific method. How do we know this property works? Well, we've tested it. We come up with an experiment. We designed a hypothesis. We tested it. We came to a conclusion, right? We know it's true. History class, same thing. Historical truth comes from the historical analysis of documents and primary resources and archaeological evidence and that kind of thing that, puts together the whole story so you know how something happened, right? The good old document-based question if you're in AP. And mathematics is the same way. And I will even go so far as to say this is a philosophical issue, right? No, truth is a whole branch of philosophy. There's a reason a lot of famous mathematicians were also philosophers, is because they were wrestling with this. They were like, okay, well, I figured this math thing out, but how am I sure? And how am I sure that I'm sure? How do I know that I know what I know, right? And like you could go on forever. But luckily, we do have a basis, especially here in a Catholic school, right? We also have theology as a unit of study. And theology's basis, its starting point is the existence of God, right? We accept that as true, and everything else in Christianity follows. We wrestle with the existence and the properties of the universe. Well, it all stems from we accept that God started it. God created the universe. There is an absolute beginning point, and everything came after that. Right? So similarly, mathematics has a beginning point. Within the realm of geometry specifically, we have those undefined terms, and we use that as our basis for the rest of it. Okay? Any questions on that concept, that structure there? No? Okay. So the rest of the section takes that structure and starts building those basic blocks of geometry. Points, lines, planes, yes. But more interestingly, right, we take segments and angles, because the segments and the angles are the real, like, water and oxygen molecules that we can build all kinds of stuff out of, okay? Rarely will we find true lines. It's just not realistic. Going on to infinity doesn't happen in the real world. But we can take a segment. And segments are beautiful because we can divide them up. We can say, hey, I can match this up to the number line, the counting system, and now we can take something that has dimension and relate it to numbers that is a counting that otherwise totally abstract. And we can take the abstract and make it physical via the number line, via the ruler postulate. Right? We started with this idea that based on the definition of the segment and stealing from number theory / algebra realm, right? The number line, right? And now I can measure all kinds of things. I can compare the length, right? How many numbers do I get to on this segment? And then we took two of those segments, say, what if you take one segment and you take another segment, right? And we connect them together at a point. And so now they're like hinged there, and now we get an angle in between. Right? Now we can talk about the angle. And between the length and an angle, we can talk about all kinds of things. We can talk about locations of things. We can talk about distances to things, relationships, and we can create shapes galore. Okay? Everything builds upon segments and angles. So that's where we need to start. And we need to have a firm understanding of everything we can do with segments and angles by themselves, even before we start building bigger and bigger stuff. So that's what our problems are going to address today. So as I go through these, I'm going to not just show you, walk you through a solution to the problem, but I'm going to try to highlight what knowledge content the problem draws off of. So let's look at our first example. A child leaves home and arrives at school after walking 6 blocks due south and 8 blocks due west. Already, we've got a lot going on. I'm going to gloss over the you have to be able to like read and understand English part. I think we can assume that that is already happening here. But we're going leaves home. We have a starting point. Arrives at school. We have an ending point. Walking 6 blocks. Oh, now we've got numerical. We've got a unit. Due south, we have a direction. 8 blocks. Due west, there must be a reason that 8 blocks due west is different from 6 blocks due south, okay? So already we're introducing length, number of blocks. How many blocks did he walk? Okay? That's length. That's based on the ruler postulate. So we need to understand that segments can be measured. Okay? Due south versus due west, direction, okay? Directions only make a difference in a plane setting when you have 2 dimensions, and comparing the relationship of those 2 dimensions is an angle. So the fact that you have 2 directions introduces angles. Now, what do we actually want to find? Find the approximate bearing. What's a bearing? Of the child's home from the school. Of the home from the school. Oh, that's different. The child left home, went to school. This is from home to the school. No. Bearing of the home from school. This is the opposite direction. Oh, so we've reversed things. Draw a diagram. Yeah, I'm almost certainly going to draw a diagram just to understand this, get a picture here. And measure the angle with a protractor. Okay. That last part's going to be a little bit tricky here because of my digital format. I can't show you how I'm working with a physical protractor. So I'm going to have to substitute a little bit. So bear with me there. That's going to lose us some accuracy here. But the first thing we need to do is create our picture. Not just any picture, but eventually a diagram. And believe it or not, you can draw more than one. I'm going to first draw a sketch to get an understanding here. Child leaves home. Let's pretend this is home. And this is school, and they walk, well, let's walk through this. Walking 6 blocks due south. Ooh, I need my directions, so we'll set up a little compass rose. Right, so we have to understand north, south, east, west. Okay, there's a bit of content knowledge there. Due south, so it goes from here south. 6 units. Okay, so maybe I need to move this. And we have to move where the school is. And then from there, right, and then 8 blocks due west. That would be this way, right? And that's 8. And so that brings us to this point here we'll call S for school. And we want to find the bearing of the child's home from school. The bearing from school. What's its bearing of home? I'm guessing that's something to do with like the distance there, or is it the angle? I don't know. Let's look up bearing. Where do we have that? Bearing, bearing, bearing. Bearing wasn't in the text, the reading. It was introduced in a problem that you will work on tonight. Yeah, this is in your problem set. Is it in tonight's, or maybe it's Wednesday's problem set? I just thought of that. I think it's actually Wednesdays. Anyways, but here it is. The bearing is nothing more than a line segment. The bearing of a line segment is the acute angle that the line segment makes with a north-south line. Ah, okay. So, compared to the compass, the bearing is whatever angle you're going at, angle from the north-south, right? So we could go this way, and here's our bearing. We could go this way, and here's our bearing. No, it said acute angle. Oh, so I would actually want to go on this side, right, to the north-south line. See the difference there? Okay, so let's go back to our problem. Now that we know the bearing is from the school, so I need of this line segment. I shouldn't have put an arrow on there, I guess, right? The segment from here to there to the north-south line. So I can either have this side or this side. Only one of those is acute. So I'll go with the top one there. I need to find that angle. Okay, that's not bad. How am I going to figure that out? I can measure it, but how do I know that I've drawn it properly, right? I could measure this sketch as is, but how do I know my sketch is any good? Is this a good diagram representation of what's going on? If my measurement is going to be accurate, I need an accurate diagram, right? I'm measuring off the diagram. So I need to make accuracy with accuracy. This was a quick sketch, right? There is no reason to believe that this length of this line here has any bearing on the number 6. No relationship whatsoever, which means even less relationship between 6 versus 8, right? There should be a relationship, the same relationship between the numbers 6 and 8 should be the relationship of length between this segment and that segment. How can I guarantee that is? I need to draw them appropriately. I need to measure them. Now, to me, the best thing to make sense is to create a grid. Luckily, on this software, I can bloop, put it onto graph paper very easily. Ha-ha, look at that. Oh, sorry. Put the camera there. So let's go over here. I need some space here. And let's go green. Let's count here. 1, 2, 3, 4, 5, 6. There we go. And 1, 2, 3, 4, 5, 6, 7, 8. Right there. So then the line we want to measure goes here. And that is to the north-south line. So let's draw that in there. Okay, so we got the north-south line. Here's the school. So we're going to try to measure this angle in here. I think that's pretty accurate. In fact, I feel like better about this diagram than if I did it by hand, because the app lets me have those like snap to perfectly straight lines, and I'm like, oh, nice. The only issue is my protractor. So since I want to measure between here and there, I'm going to set up my protractor to be sideways, right? We're going to take our little protractor, and it has a little markings on it, and I'm going to pick it up and, hold it over there and put the center right on that vertex, right? That's how we measure with a protractor. Except I need to make a better protractor. How can I make a better protractor here? I got to work with the tools I've got. So at this point, all that's left to actually solve the problem presented is to go ahead and measure my nice, neat diagram. I've put on myself a secondary problem of using this app without a proper protractor. So I have to create a protractor from scratch that is still somehow reliable. I can make a perfect circle. That's pretty decent, okay? And that's a good starting point. So I'll start with that. And there is my center point, I think. How is that for the center? Yeah, right there, okay. And so I know right here would be 0 degrees. And I know straight across here would be 90 degrees. I can at least see that, yes, in fact, this will be an acute angle. It is between 0 and 90. Exactly how much? That's what we got to find. There is only one good thing I can do with this. This does have let me see if I can find it, snap feature of 45s. I think it's getting thrown off by the grid. So let me turn the grid off for a moment. There we go. It will snap a 40, whoops, straight line. And I think there it is. Oh, lost it. Okay, so I know that's 45. That's what the computer can give me. Now, human-wise, the best thing I can do is humans are really good at dividing things in half visually. Thirds, not so much. Fourths, fifths, anything, even worse, okay? But we can divide in half pretty good. So I'm going to approximate, there's half between 45 and 90. There's half between 0 and 45. And I'm going to go one closer in between all of those. There we go. So there's my halfway and quarter marks. So the smallest level would be 1/4 of 45. So just real quick, 45 divided by 2 would be 22.5. And 22.5 divided by 2 is 11.25. So that's the most accurate I will be with this protractor. Let's find out here. Oops, let me move up a little bit. There we go. Get the whole thing on screen. And then grab my whole protractor here. We'll line it right there. Ooh, that looks really close to this mark. So now I got to estimate how much more past the 45. Is it the full 11.25 degrees? I don't know. I don't think so. That doesn't quite look like the full 11.25. So why don't we round that off to 10? Right? We'll say not quite a full 11, 10 more degrees. Is that fair enough? That angle there is going to be 45 plus 10 more, 55 degrees. That's about as confident as I'll get it, right? And I'm sure I'm not more than 5 degrees off. That would be, extreme. Maybe within 1 or 2 degrees. I'm pretty happy that it is probably between less than 57 degrees, but more than 53 degrees. Right? That's going to be, because I'm estimating here, right? I'm doing the best with the most accurate protractor I can have. You're never going to be perfect anyways. So it's good to have an idea of okay, how accurate can I get? I don't have a protractor that measures down to the single degree, okay? But I can definitely say that this is more than half of 11, right? I'm more than 6 away, okay? But not quite 11 away, so. Any questions then on how I approach that problem? I did try to make sure your problem tonight and even for Wednesday did not actually require you to measure by hand. So don't worry if you don't have a protractor at home. Okay, next problem. Standard clock face. Okay, this is classic math problem set up right here. We mathematicians love our analog clocks, so much good stuff going on. Let's take a look at what they're asking for us in this one. So just a reminder, clock is divided into 12 hours, so each hour from 12 to 1, 1 to 2 is 1/12, and then there are 60 minutes all the way around. Okay, so the question is, after 1 hour, through what angle has the hour hand rotated? Okay, so this guy here, the short one, points to the hour from 1 hour. So from 2 o'clock to 3 o'clock, it goes from here to here, right? It has moved 1/12. We can at least deduce that from the way the clock is set up, right? After 1 hour, the hour hand has moved 1/12. 1/12 of a full circle. How many degrees is that? A full circle, we know by definition, is 360 degrees. Right? Again, that was something we defined. We had to create an increment. We picked out the degree because it's a very convenient number. There's some historical reasons behind that number as well, but it works pretty well. And thus, 36 divided by 12 is 3, still power of 10, so we get 30 degrees per hour. Okay. What about the minute hand? A full hour has the minute hand going all the way around the clock, right? Okay, all the way around the clock is 360. So there's not even much thought or computation required for that. The minute hand is 360 degrees around. Okay? So this is for the hour hand. Or let's say 30 degrees per hour, 360 degrees per hour for the hour hand, and this is for the minute hand. Let's go on to B. After 1 minute, through what angle has the minute hand rotated? Oh, same with like hour, hour hand, minute, minute hand. Okay, so 1 minute goes by. Well, how many minutes in? They already said the whole clock face divides into 60 minutes. So it has moved 1/60 of that. The minute hand goes around a 60th of the whole clock, which the whole thing is the 360. So 36 divided by 6 is 6 degrees per minute for the minute hand. How about the hour hand? Right, that's what they asked next. The hour hand after 1 minute. So the hour hand in an hour goes 1/12, right? The 30 degrees. A minute is a 60th of the hour. So in 1 minute, the hour hand moves a 60th of this, right? Minute hand moves a 60th of the whole thing. Hour hand moves a 60th just of that segment from 2 to 3. That 30-degree sector. So we still have 1/60th, because we want 1 minute. But now it's a 60th of 30 degrees. Right? 3 over 6 reduces to a half. This is 0.5 degrees per minute for the hour hand here. Oh, right. Okay. Interesting to think about, right? I don't know if you've ever watched an analog clock and thought about it. Okay, exactly how far? Because the hour hand It has to get around to the 3 eventually, but it doesn't just, as soon as it goes 2:59, 3 o'clock, the hour hand doesn't jump and go, whoop. Now it points at the 3, right? It's slowly going, half a degree a minute, updating itself, ticking along. All right, so now with that basic information, now we can answer the more interesting question. And that is the measure of the obtuse angle formed by the hour and minute hands at 9:10 and 5:56. Ooh, okay. So here's what I'm going to do. I want to draw a picture because I want to see this visually, right? The analog clock is a very visual representation. And I'm looking for the angle between the hands, okay? I already know a little something about how the angle compares to the time passed, right? That's what all this was. The time, the ticks of minutes, number of minutes from this mark on the clock to that mark on the clock correspond to how many degrees. So I can convert that. So if I can tell where each hand is on the clock and how many hour and minute marks are in between them, I can turn all of that into a number of degrees, right? So this is thinking it through, simplifying in a way, taking, instead of counting the degrees, I'm going to count the minutes from one hand to the other. So let's start with 9:10. All right, I need a basic clock. So 12, 6, 3, 9. And so the hour hand is there, well, mostly at 9. It points off, a little bit above, a little bit past that, right? Because it's past 9 o'clock. It's not perfectly 9 o'clock. And then 10 will be, well, here's 1, here's 2. So 10 minutes will be there. This says the obtuse angle, which is this one here, right? The other side would be the reflex angle, more than 180. Okay, so let's fill in our other numbers here. This is 10, this is 11. This isn't quite to the 10 yet, right? We know that. It can't possibly be at the 10 yet, because then it would be 10 o'clock, and we're not there. So the question is, how far away, right? Think about a simpler case. 9 o'clock exactly would be, the angle would be perfect 90 degrees. Except I have to go out to 10 minutes past that, so I need to add 10 more minutes. 10 minutes from the minute hand is, what did we say? 6 degrees per minute for the minute hand, right here, right? So times 6 degrees per minute, minutes cancel out, and that's going to add 60 extra degrees. Okay, so the minute hand has gained 60 degrees from the 9 o'clock position, the 90 degree 9 o'clock position. I've got 60 more to go. But the hour hand has also moved up. So I've lost some degrees, right? It's now up here. I've lost some. How much have I lost? Well, I've lost 10 minutes worth of the hour hand. How much does the hour hand move? Hour hand moves half a degree per minute. So I'm going to multiply by 0.5 degrees per minute. Minutes reduce. 10 times 0.5, half of 10, 5 degrees. So this is a 60 degree gain. This is a 5 degree loss. Does everybody see that? I'm going to assume your silence means yes. So we go from 90 degrees at 9 o'clock plus 60 degrees for 10 minutes minus 5 degree loss from the hour hand also moving 10 minutes. And so 90 plus 60 is 150, minus 5 is 145 degrees. Not too shabby, right? How about the other one? The other time is 5:56. 5:56. Okay, let's look at it on the clock. So from the center, I've got 12, 6, 3, 9, 5:56. So here's 5 and 4. Here's 10 and 11. So the minute hand is almost but not quite to 12. And the hour hand is almost but not quite to the 6, right? We're 4 minutes short of 6 o'clock. Okay, and I need, take a look at this, right? Here is, oops, I'm going to go over a little bit. There we go. There's perfect 6 o'clock. Now, my angle that I want is actually on this side this time, okay? From 6 o'clock, it would be a perfect 180 degrees, right? So I need to adjust from that 180. Just like I said from 9 o'clock, hey, this is 90 degrees, and I've gone, how much? I think it's easier to say, well, this is almost 180, but I'm off by a little bit, and we can make those adjustments. But I already did that. So for the sake of example, let's try a different tactic. Let's go in a different way. Let's see if we can do it from scratch. So let me clear out the red here. And instead, I'm going to have these tick marks. We still need 8 and 7. How many hour segments are between here and there, right? I have hour segments from 11 to 10, 10 to 9, 9 to 8, 8 to 7, 7 to 6, and I can't go 6 to 5, right, because that would go past the lines. So I have these segments, 1, 2, 3, 4, 5, right? So I have 5 full hour sections, and we know each hour is represented by 30 degrees on the clock, right? So with that, we get 150 degrees. Now what we need to do is that was to this mark. Now I need to add in this bit and add in this bit, right? The minute segments. So how far away is the minute hand? That's always the easiest. It was 5:56. Okay, 55 would have been on the 11. So it's 1 minute past the 11. So the minute hand has moved 1 minute. So it's 1 minute times how many degrees? 6 degrees per minute for the minute hand. Okay, so I get 1 6-degree addition. How about for the hour hand? It is how far away from the 6? I don't know how far from 6. So I've got to count backwards now. How many minutes away from 6 o'clock am I? Right, this is 4 minutes till 6 o'clock, right? So that means the hour hand is 4 minutes away down here. So that's going to be 4 minutes times hour hand moves 0.5 degrees per minute. So 4 times a half is 2 extra degrees. So now we add those all up. 150 plus 6, 156, 158 degrees. There's my final answer. Any questions on how we did that? No? All right, then how are we doing on time? Up, there is the sound. We've got 5 more minutes. Okay, go ahead, look over your problem set for tonight. Read the whole thing. Just skim, no, more than skim. Read through deeply and consider yourself like, okay, could I do this one? What do I think? Like, make a judgment call. What's easy? What's hard? Right? Find the hardest ones for you and start them tonight. So tomorrow, we dedicate our class time tomorrow to working on them. You can ask me questions in class of, hey, Mr. Apple, I tried starting this last night. I took a look at it. I'm not sure I understand the problem in the first place, and that's throwing me off. I don't know where to start. You can ask me those questions, okay? And make that time as useful as possible for you.